Good morning, dear students. In the last video, we have seen about homogeneous equilibrium and how to calculate equilibrium constant for the concentration and equilibrium constant for pressure for the homogeneous physical state reactions. Now, today we are going to discuss another topic that is about heterogeneous equilibrium. When we say heterogeneous equilibrium, it means the equilibrium system is in not a similar state. In homogeneous, we were having that reactant were solid, they give product also solid. If reactant gas, they give product also gas. If reactant liquid, they will give product also liquid. But here, equilibrium in a system having more than one phase is heterogeneous equilibrium. So here you see H2O in a liquid form. When heat is given, it gives a product into H2O vapor form, that is gaseous. So liquid to gaseous, both the states are changed. Product is gaseous whereas reactant is liquid. One more example, calcium hydroxide in the solid form when reacts with the water aqueous gives calcium plus 2 aqueous and 2OH minus, that is hydroxide aqueous. Solid here, one of the reactant is solid and the products here both are aqueous. So now when reaction is heterogeneous, then the molar concentration of solids and liquids, when heterogeneous equilibrium is there, mixture is heterogeneous, and in heterogeneous, when the reaction is carried out among solids and liquids, then as they are tightly packed, solids are very tightly packed, less intermolecular space in liquid than gas, they have constant, and on the other hand, the molar concentration of gases and liquids vary. When the reaction is taking place between solids and liquids, the molar concentration remains constant even before and after the reactions because the molecules are tightly packed. And when the reaction is taking place between gases and liquids, then the molar concentration vary. So this we have to keep in mind. So molar concentration of solid and liquid are independent of the amount. When solid and liquid is there, they are independent of amount. Whatever the amount is taken for the reaction, they have no bar for it because before and after their concentration remains constant. So if I say X is some substance in a solid form and X is some substance in a liquid form, then you see square bracket. Then their concentration, that is molar concentration, moles per liter, is equal to constant. And molar concentration of gas and liquid depends on amount because gas has a very large intermolecular space and they can randomly move from a respective place to other place, and so their concentration, gas as well as liquid, when they are reacting, because of the gas, one of the reactant, the concentration will vary. Let's have an example here. Calcium carbonate on giving heat, that is thermal decomposition takes place. It's in solid form. It gives calcium oxide in solid form but carbon dioxide in gaseous form. Right? So now what happened? I want to calculate equilibrium constant at constant concentration. So Kc is equal to concentration of product CaO into CO2. No coefficient stoichiometry, so no power, divided by calcium carbonate reactant. Now here you see calcium oxide is in solid, calcium carbonate is in solid, carbon dioxide is in gaseous form. So equilibrium constant for heterogeneous reaction has to be modified. Why to be modified? Because I just told that solid and liquid remains constant even before and after the reaction. So, we have to modify it as molar concentration of solid and liquid before and after reaction remains constant. Therefore, calcium oxide in solid form and calcium carbonate in solid form has to be ignored. And when they are to be ignored, the equilibrium constant will be modified. And modified equilibrium concentration is concentration of this and this both is to be ignored because their concentration is constant. No need to take its ratio value. So here Kc is equal to CO2 in a gaseous form. And as partial pressure of calcium oxide in a solid and calcium carbonate in a solid do not change because they are considered in a pure states, and as they are in a pure state, their pressure effect is also not observed, and that is why the equilibrium constant for the pressure is equal to partial pressure of CO2 in a gaseous form. So there also both solid form is to be ignored. The value of Kc, equilibrium constant for concentration, can be calculated by substituting the concentration terms in mole per liter. And for equilibrium constant for pressure, partial pressure, that means the pressure of each respective reactant and product, that is partial pressure. So equilibrium pressure depends on the partial pressure which is substituted in Pascal, kilopascal, bar or atmosphere. It is also observed that any equilibrium is established at fixed temperature, because if temperature keeps on varying, increasing, decreasing, then the reaction which is taking place, the reactant and the product will not attain equilibrium, because with the increase in temperature, the rate of reaction increases. With the decrease in temperature, the rate of reaction decreases. And so there will be the variation in the formation of product from the reactant and even in the variation of the backward reaction, that is from product to the reactants. So to attain the equilibrium for the respective reaction, the temperature is to be fixed. And for in that relation, for the above reaction of thermal decomposition of calcium carbonate, that is equation 1. At constant temperature, that is at 1100 Kelvin, partial pressure of CO2 in a gaseous state is, partial pressure of CO2 is 2 into 10 raised to 5 Pascal. Or we can say there is a constant concentration of CO2 in equilibrium with calcium oxide and calcium carbonate. So, equilibrium constant for the pressure is equal to partial pressure of CO2 in a gaseous form, which is equal to 2.0 into 10 raised to 5 Pascal. But with the variety of reactions and experiments, it has been observed and it has been considered that Kc is not preferring to have unit, and it is possible to have Kc dimensionless or unitless only when reactions and products are in their standard states. That means mostly it is observed and it is deduced that Kc and Kp should be dimensionless, because all the time the unit does not remain same for the respective reactions because of the heterogeneous equilibrium. And if that is to be attained dimensionless, it is only possible that reactants and products should be in the standard states. Why standard state? Because in a standard state, the pressure of any substance is a 1 bar, which is fixed, and 1 bar is 10 raised to 5 Pascal. So in a standard state, equilibrium constant at pressure is equal to partial pressure of carbon dioxide is equal to 2 into 10 raised to 5 Pascal divided by 10 raised to 5 Pascal, because for the standard state. This is to be considered for the standard state, so it will be 1 bar, and 1 bar is equal to 10 raised to 5 Pascal. And so here you see Kp is not having any unit. So Kc and Kp are preferred to be dimensionless. Why? Because for all the reaction due to stoichiometric concentration, the unit does not remain same. Thus, units of Kc and Kp depends on units of stoichiometric coefficients of the pressure and concentration in which they are measured. If measured in Pascal, then it will be Pascal. If bar, then will be bar. Right? If atmosphere, then will be atmosphere. But concentration will be mole per liter. Let's take an example here. H2 gas reacts with I2 gas, give hydrogen iodide. Here, stoichiometric concentration is 1 mole, but here it is 2 mole. So, in terms of concentration unit, Kc is equal to Hi raised to 2 upon H2 raised to 1, I2 raised to 1. Now, concentration unit is mole per liter. So, Hi raised to square, that means mole per liter raised to square. Mole per liter, mole per liter. So, mole per liter square, it means mole per liter into mole per liter. So, this will be cancelled. And for Kp, atmosphere raised to square, atmosphere into atmosphere. Suppose pressure is in atmosphere. So, it will also cancel. Thus, Kc and Kp has no units. Or we can say here, for hydrogen and iodine reactant, hydrogen iodide gas, the Kc and Kp is dimensionless. Let's have another example. N2O4 reacts and gives twice NO2 gas. Both is in a gaseous form now. Let's see, Kc is equal to NO2 raised to 2 upon N2O4. So, mole per liter square upon mole per liter. Here it is mole per liter square. So, mole per liter into mole per liter. So, 1 will be cancelled, and here Kc is not dimensional net, it is mole per liter. In the same way, if atmosphere pressure is in the bar, then this will be bar square upon bar, so it will be in a bar, right? But for standard state, P is fixed 1 bar and concentration at 1 molar. So for, let us see an example. If pressure of a gas in a standard state is 4 bar, then 4 bar for a standard state will be considered as fixed 1 bar. So 4 bar divided by 1 bar will be 4, that is dimensionless. Or if it is 4 mole per liter, then 1 concentration, 1 molarity, it means 1 mole per liter. So it will be also only numeral value 4, right? Let us see one more example, purification of nickel. When nickel is reacted with carbon monoxide gas, what happens? We get nickel tetracarbonyl, NiCO4. This is in the solid form, this is in the gas form, this is in the gas form. So now pay attention here what happens. Kc is equal to NiCO4, no stoichiometric coefficient, so no power. Here Ni concentration, here CO concentration raised to 4 because 4 is the stoichiometric coefficient which shows the mole of the carbon monoxide gas. Now as just discussed, that heterogeneous equilibrium, it means the reactants and products, they will be in more than one phase. And here you see nickel is in solid and carbon monoxide is in gas, but the product is only in the gaseous form. And as I just discussed here in this video, that for solid and liquid, the amount or the substance which is reacting, which is in the solid and liquid form, they are free, they are independent of the amount. Their concentration before and after reaction remains the constant. So we are in need to neglect them. So here you see this is in the solid form. So solid to be ignored. So what will be the Kc? Kc will be NiCO4 concentration gaseous form and carbon monoxide raised to 4 gaseous form. This is to be ignored, right? And one more example, Ag2O silver oxide in a solid form reacts with HNO3 in aqueous form having 2 moles, gives 2 moles of silver nitrate HeNO3 in aqueous form and H2O liquid. So looking to this reaction equation form, this is solid, this is liquid. Both has to be ignored. So if you now remember this, you can directly go for this step also. But if you have forgot, then first write this, what we have already learned. Kc is equal to product of the product divided by product of the reactants. So here it is AgNO3 raised to 2 multiplied by H2O upon Ag2O multiplied by HNO3 raised to 2. But as I told, solid and liquid is to be ignored. So Kc will be AgNO3 raised to 2 divided by HNO3. So in numericals also when we are calculating, we have to keep this in our mind that when solid and liquid is there, their concentration is to be ignored, right? And only the concentration of gas and aqueous that is to be considered. So this is about the heterogeneous equilibrium. The calculation of Kc and Kp is completely similar as homogeneous equilibrium. But the thing you have to keep in mind is in heterogeneous equilibrium reaction, we have to neglect we have to ignore the concentration of solid as well as liquid, right? Because they are always in the standard state before and after the reaction. And standard state of the particular substance, pressure is always 1 bar and concentration is always 1 molar. Clear? So this is about homogeneous and heterogeneous equilibrium. Right? Thank you.